Hey Chem Kids, this is Underwood coming at you with another webcast. Today we're going to be talking about chemical kinetics. It's going to be a little discussion about reaction rates and equilibrium. When a reaction proceeds, remember we put two reactants or more together and they react together, and because they're reacting together, they're being used up, and so their concentration is going to go down. The products, on the other hand, are being made, and so the concentration of the products is going to go up. We can look at this example right here. We have A and B are two reactants, and as they're reacting together, their concentrations are going to go down. And if we look at C here, it's our product, it's being made, and so we know that the concentration is going to go up. If we look at a real-world example, let's say we take a little bit of a H2, a little hydrogen gas, a little oxygen gas. We can go ahead and combine those two to make some water, very important molecule to you and I. There we go. Now when we take our hydrogen gas and we take our oxygen gas, and we put those two bad boys together and they react, their concentrations are going to go down. But as we're making water, our product, its concentration is going to go up. Makes sense, doesn't it? Now we can talk about reaction rate. And what reaction rate is the change in the concentration of the reactants and the products in a chemical reaction per unit time. Any rate, we're talking about something that's happening over a period of time. And in our case here, we talk about seconds. If you guys want to take a peek at this graph right here, we see we have our concentration, and at the top here we have a concentration of our products, of our reactants. They haven't started reacting together yet, so their concentrations are high. And we have the concentration of our products here at the bottom. The products haven't begun to be produced yet. Now as time progresses and that reaction happens, we see that the more products are being made and our reactant concentration is going down because they're being used up. Pretty straightforward. Now if we go back in time a little bit, we can remember what we call chemical equilibrium. Remember we told you that some reactions will actually happen in the forward direction, and some are going to happen in the reverse reaction as well. Now when the rate of the forward reaction is equal to the rate of the backward reaction, we say that we have reached chemical equilibrium. Keep that in mind. There are going to be some problems on the worksheet tomorrow that are going to talk about chemical equilibrium. You're going to have to reach back when we talked about Le Chatelier's principle, see if you can answer those questions. So, therefore, we can in fact change the rate of reaction. We can increase and decrease the rate of reaction however we want to. But one thing we need to think about is this idea called activation energy. So, what's activation energy? Activation energy is the minimum amount of energy that needs to be supplied to a reaction for it to proceed. As you can see, this guy over here, he wants to push this boulder down the hill, but he has to overcome, or he has to add his own bit of energy to get up over the hump. We can go ahead and translate that over to this example over here. Notice, we have a graph here with the energy and the reaction coordinate, or whether it's reactants or products that are present. If we want to go from reactants to products, we can't just go in a straight line like that. No, instead we have to supply a certain amount of energy to allow that reaction to occur. This energy here is called our activation energy, the minimum amount of energy that's required for a reaction to occur. Now for a reaction to occur, you have to realize that molecules and atoms actually have to crash into each other. They have to collide. And so we can do certain things to the reaction environment that make it more likely for atoms and molecules to collide and react with one another. Well, you say how? Well, there are a couple different ways. The first, we can increase and decrease the concentration of reactants, and that will manipulate the rate of reaction. If we add more reactants, you know that we're going to have more stuff, and more stuff equals more collisions. The more molecules and atoms that I have in a reaction is going to equal more collisions, and it's going to increase the rate of reaction. We can also change the temperature of the reaction. If we increase the temperature of the reaction, we're increasing the average kinetic energy of the reaction. If you guys remember from our thermodynamics unit, that the kinetic energy is the velocity or the energy of movement. So if we increase the average kinetic energy of the molecules and atoms that are in a reaction, there's going to be more likely collisions. And when we have collisions, we have a reaction. And more collisions equals a higher rate of reaction. We can also use catalysts, and catalyst is maybe a new word for some of you, but a catalyst actually lowers the activation energy. If I was to draw a picture, a little representation of that graph we saw before, we can have energy over here, and we can have our reaction proceeding here. Now when we start at products, we give the activation energy, and then the reaction proceeds to completion. But when we add a catalyst being a chemical or an element or another atom or another compound, something that allows the molecules and atoms to come in cleaner contact with one another, that actually lowers the activation energy. And so we could then rewrite this little graph, and with a catalyst it actually lowers that activation energy, and so less energy is required for that reaction to occur. And when we have a catalyst allows for more collisions, and when it allows for more collisions, we're increasing the rate of reaction. Now we can go ahead and do a little bit of practice now that we've talked about reaction rate and equilibrium. If we have a change in these different conditions down below, will it increase the forward rate of the reaction? This reaction right here is a very common reaction, a little nitrogen gas, a little hydrogen gas coming together to make ammonia. Now if we add more nitrogen gas, what's going to happen? Adding more reactant, we're adding more stuff, we're increasing the chance of collisions. So will this increase? The answer is yes. Now if we take away some ammonia, we're taking away ammonia as it's being produced. That's going to make the reaction want to occur and continue to go forward. So is that going to increase the rate of reaction? Absolutely. Now if we increase the temperature, remember increasing the temperature increases the average kinetic energy of the reaction. If the molecules and atoms are moving faster, there's more of a chance of collision, or collision with enough energy, and this is in fact going to increase the rate of reaction, so that is in fact yes. And if we add a catalyst, which is a chemical that is put into a reaction that allows for those molecules and atoms to come into contact with each other more easily, this is in fact going to increase the rate of reaction. Remember, a catalyst itself is not going to be used in the reaction. It is just used to help the reaction. Now, I really hope that this video was helpful. Please move on and take the Moodle quiz, and we'll see you guys tomorrow.